Hello and welcome everyone to Aviatrix Deep Dive with Saad. In today's session, I'll be discussing about the Aviatrix technology called ActiveMesh. So what is ActiveMesh? ActiveMesh technology provides network resiliency with high performance. It also improves your convergence time too. So let's talk about this thing in detail, right? As I have been discussing in my previous sessions, then in every single cloud network, doesn't matter whether it's your VCN, VPC, or VNet, there are two gateways, Aviatrix spoke gateways or transit gateways at a given time to provide the high availability. So if I'm going to draw that, let's say it is my GCP environment, I have a VPC here and VPC here. So these becomes two spoke VPCs. And here is your transit VPC right over here. Two spoke gateways and then a connection between them, spoke gateways and a connection between them, and same thing over here with the transit, right? So every VPC, spoke or transit, is going to have your two gateways. And then each gateway is going to build two tunnels with the transit. So if I'm going to draw these tunnels right now, let me use a different color. Primary spoke gateway is going to create one tunnel with the primary transit, and then the same gateway is going to create another tunnel with the transit HA gateway. The spoke HA gateway is going to do exactly the same thing. It is going to create one tunnel with the primary gateway, and then another tunnel is going to be created with the HA transit gateway. So what is going to happen on the other side? The spoke number 2, pretty much the same thing. Primary is going to create two tunnels, and then the HA is going to create the two tunnels. So as you can see, there is a mesh of these connections over here. So this is the technology that we call it the ActiveMesh over here. Both gateways, which you see over here, pass the traffic at the same time in active manner. Number of spoke gateways and then the transit gateways, as well as their instance sizes, are independent of each other. What do I mean by that? It means you can have hundreds of spoke gateways while you will have few number of transit gateways, because transit gateways becomes your aggregation point. And then the size of the spoke gateways could be small, while the transit gateways are typically bigger than the size of the spoke gateways over here. So they are independent of each other. This ActiveMesh technology that we just talked about it, this is enabled by default, so you don't have to enable it, right? And you actually don't have a way to even disable it. Why would you disable it? Because this is something which you needed in your network architecture. So what are the use cases? One use case, I just talked about it over here, which is, let's say if this is any cloud, does not matter which cloud we are talking about, and if this is a region 1, then you just take a look at it. This provides the communication between the applications sitting in different VPC, VNet, or VCNs. Let's say this is region 1 and cloud 1 or CSP 1. Now, if we wanted to draw it out a similar architecture, this time I'm just going to draw just a transit over here, and this transit could be in region 2 or cloud 2 or CSP 2. Again, two Aviatrix gateways, and what they are going to do, they are going to form a mesh also. Like, it's going to have a connection with the primary gateway, and if I'm going to just create a gateway like this over here, and it's going to create a tunnel with the HA gateway also. The transit again, and this transit is going to create with the the primary, and then the HA is going to create another tunnel with the HA gateway. So first use case is all about intra-region. Now we are going either inter-region or multi-cloud environment where transit can also create an active mesh between each other, the way I just described. What else? What is the other use case? For example, if you have a on-prem connectivity, like any kind of hybrid cloud connectivity. So if I'm going to draw a on-prem environment, it could be your partner side, it could be anything. It could be your branch, it could be your data center, it could be anything. Now if I want to move back this transit gateway, let's say I'm going to draw one more transit over here. This is Aviatrix transit. Then if this is an on-prem router, what it's going to do, it's going to create a connectivity pretty much the same way as we have been describing. Going to create the active mesh between the on-prem and that as well. So what about if you have the Aviatrix edge, Aviatrix, secure edge? So if I'm going to draw one more transit, this time the connectivity is not with the third party, but with Aviatrix edge devices. So I'm going to call it edge. Then we are going to create again the active mesh over here. Now a difference in this scenario is it's not going to be 4 connections, it's going to be n number of connections here, and these n number of tunnels basically going to depend on the size of your transit gateway. So that is going to be the difference. While everywhere else, since I'm using the standard encryption, by default it's going to create the 4 connections from each VPC, VNet, or VCNs over here. And same thing between the transits too, unless we use high performance encryption, or we also call it insane mode. I'm going to erase this so we can understand the route classification using a different diagram. Alright, so let's talk about the Aviatrix route classification, how Aviatrix controller classify the routes. There are 2 different types of routes Aviatrix controller understands. One is the local routes, and the second one is the BGP learned routes. Let's talk about all of them. First, I'm going to draw in TGW. Basically, somebody is using Aviatrix controller to orchestrate the TGW, attaches a VPC without the Aviatrix gateway. When you attach, this must have some kind of a CIDR information. So the routes that you attach to that, it is considered as a locally learned route at this point, right? And what is the value of this thing? We will talk about in the next section. All right. And what about when you have, let's say, here, I'm going to draw an Azure environment. In Azure, you have a VNet with the Aviatrix spoke gateways here. When you attach that to Aviatrix transit gateways, something like that, that connection or that attachment is also going to be, we are going to call the routes learned by this is also considered as the locally learned routes. If you have, this is the Azure environment, right? Let me draw one more environment over here. Let's say a GCP. And you have 2 VPCs over here. Both have Aviatrix spoke gateways. And here, transit gateways. And you are attaching both. So the routes learned in this scenario are also going to be considered as the locally learned routes. Now, if you have an Azure, since this is the Azure environment, that's my GCP, and this is AWS environment. Now, if let's say if you have a native spoke attachment to the Aviatrix transits, so you can see there is no Aviatrix gateways over here, then even this attachment is going to be considered as a locally learned route over here. All right, now let's talk about if you have a static connectivity. For example, you have an on-prem, right? On-prem, you have a router, on-prem router, and you connect this to Aviatrix Transit. And you are not using here any of the dynamic routing protocol, but instead you are using a static routing over here. In that kind of scenario, what transit gateways are going to consider that kind of a learned route as also locally learned routes. So we are talking everything in terms of the Aviatrix transit at this point, right? So this is also going to be considered as a locally learned route. How about the firewall, right? Let's say if you have some firewalls over here and you have enabled a feature which is egress through firewall. So if you have, for example, if you want, this is internet, if you want all your spokes, in order for them to go through to internet, they have to go through the firewalls. Then what you have to do, you have to actually propagate the quad 0 route out. So there is a feature in which Aviatrix controller is going to propagate that quad 0 route. We call it egress through FireNet. So what happens then, all the spokes are going to receive this quad 0 route and then sensor traffic, which is internet bound traffic, over to the firewalls, and firewalls are going to send the traffic to the internet. So this quad 0 route, which we are talking about, that is also going to be considered as a locally learned route. And what about these transit addresses space, or the transit subnet, or the CIDR information? For example, if this transit has a address space of 10.0.0.0/23, then it is also going to be considered as a locally learned route. By the way, locally learned route has higher priority than any other route, which is a BGP is the other route. So same thing over here in this scenario too. If you have enabled any kind of source netting, right, on the transit gateways, then that source net IP, for example, if I have enabled a source net, and that IP could be any IP, 192.168.1.10, for example, that particular source net IP is also going to be considered as a locally learned route. Remote transit gateway peering. For example, if you have the transit gateways, they are connected to each other, which is the transit peering between them, then this transit peering, is we are going to classify as a BGP learned route. Just remember one thing, there is no BGP running between the Aviatrix gateways at all, right? Why are we calling it the BGP? Because transit gateways might be receiving some of the on-prem routes using the BGP. It actually receives the BGP attributes, and not only receives it, it applies all the traffic engineering on it, and then also propagates the BGP attributes to its neighbors also. So for a better route classification, we consider the connectivity or peering between any transit gateway as a BGP learned prefixes. For example, if these transit gateways are sending any routes to these transit gateways, then we are going to consider them as a BGP learned routes. Okay, so what about if this TGW is attached or connected to on-prem using some kind of a direct connect, right? So in order for this thing to be connected to the direct connect, then definitely there is going to be a DX gateway in the middle, and it's going to be connected like this. And this communication is also going to happen using the BGP. So the routes learned on the TGW side at this point are going to be considered as a BGP learned routes. What about if you have another on-prem environment, and this time you are actually creating an IPsec tunnel or a VPN tunnel with the TGW. This tunnel is again going to be using the dynamic routing protocol. We are going to consider this as a BGP learn route too. Any other site to cloud connection means hybrid connectivity from your cloud to on-prem. This connectivity could be using the Aviatrix Secure Edge, right? Edge over here. Or this could be like any other branch with any third-party routes. Remember, this one was using the static, and now I'm talking about the BGP over here. So if this is using the dynamic routing protocols like BGP, then we are going to call this route as a BGP learn route. And this connectivity with Aviatrix edge devices, that is also considered as either BGP if this is Edge 1.0. If this is Edge 2.0, then at that point it is going to be considered as a locally learned routes. Okay? Because there is the software-defined routing in between the edge devices and then the transit gateway at this point. Okay, so now let's talk about what is going to be the route selection algorithm. We have to learn this thing first in order to understand our route selection algorithm. All right, so let's talk about the route selection algorithm here, right? So the first thing is longest prefix match, right? So if you are learning multiple routes, for example, here we have the BGP over here, and then you are advertising 10/8 over here and 10/8 over here, right? And then 10/8 in this direction too. Okay? The transit gateway is going to receive this thing. These both prefixes are pretty much the same, but let's say if this is 10/24, the first one is 10/24 and this one is 10/28 at that point, or 10/8, then definitely the longest prefix match is 10/24, and it's going to, our transit gateway is going to prefer that route, which is the basics of the networking. So if the length is equal between the BGP learn routes and then the local run routes and all those kind of things, then the local run routes are going to be preferred for sure. If the routes are same length as you can see over here, then in the case of the BGP, the AS path is going to be the tiebreaker basically at that point. So the shortest AS path length is going to win. For example, if this 10/8, we are learning on this transit gateway AS path length of 2, while this one with the AS path length of just 1, then we are going to prefer this particular guy. Let's say this is a branch and this is a daisy. So we are going to prefer the branch over the data center route in this scenario because of the AS path length, and everything else was pretty much the same at that point. So if I wanted to write it down to have this, better understanding of that. So the first one is about longest prefix match, right? And then we are talking about if both are equal, then at that point, local route is chosen. Local wins. And then if routes are same type, like for example, BGP, at that point, we are talking about then what is going to happen? The AS path length, right? Shortest win at that point. Okay, what happens if AS path lengths are same as well, are equal, right? Then at this point, we are going to utilize the lowest metric. Whatever metric is lowest, which is received from the on-prem environment, we are going to use that thing as a tiebreaker at this point. Okay, so what is going to happen if even not only that, but metrics is also same, right, or equal between the two routes, like 10/8, both receive using the BGP, both have the same AS path length of 2, let's say, and then the metric is same. At this point, what are we going to do? There are a couple of things at that time which we have to consider. So the first thing is we have to see whether ECMP is enabled or disabled. If ECMP is enabled, at that point, it's pretty much very easy for us at this point, because we are going to distribute it to all available paths at that point. If ECMP is disabled, at that point there is certain things which we have to consider, right? So what are those things? First of all, let's say I'm going to draw it out over here. Aviatrix transit, and then we have, let's say, 2 on-prem, 2 different routers, and we are going to have the connectivity like this. Let's say you are sending 192.168.3.0/24, and you are advertising this way and that way. Since ECMP is disabled, we need to find out like which route Aviatrix Transit actually programmed it first. For example, let's say if this is a branch 1 or partner 1, this is the branch 2 or partner number 2. If this connection came in first, then we are going to program the route 192.168.3.0/24 from B1. If both of these connections are online at the same time, at that point we are going to consider the lower integer IP of the next hop, right? So for example, this guy's IP is I don't know, 100.1.1.5, while this guy is 100.1.1.10. If both came in at the same time, then B1 is again going to be the winner in the scenario because it has the lower integer of the IP next hop. So that is our path selection algorithm for ActiveMesh. So it is very critical for us to understand, first of all, what is going to be the classification factor, route classification criteria, and then we need to understand this path selection algorithm based on that. So remember again, so 2 different types of routes, either locally learned routes or BGP learned routes. And then the path selection algorithm is defined this particular way. All right, so let me erase this thing. When I come back, I'll draw another diagram, and then we understand this path selection algorithm in detail. All right, so now I'm going to draw a multi-cloud network architecture. Here you have Aviatrix spoke and transit. There are going to be at least 4 connections. So I'm not drawing all those 4 connections. I'm just letting you know that these are 4 connections over here. And if we are going to draw another transit architecture with a couple of more spokes over here, and then again, these are ActiveMesh connections, like 4 connections. And then these transit-to-transit connectivity, these are also like 4 connections over here, right? So this is all ActiveMesh over here. Now, if we have an on-prem environment, and let's say you have 2 on-prem router over here, and you have another DC, right? And then you have connected it to the Aviatrix transit like this, right? And again, this is a ActiveMesh environment. All right, in order for you to have some kind of connectivity between the data centers, there is some sort of, MPLS or something else over here too. Now, you are advertising, let's say 10.0.0.0/8 from here, and same thing on this guy too. This would help us understand the path selection algorithm. These routers could have ASN of 65,000. This guy, 65,001, right? Aviatrix Transit Gateway, let's call it 65,002. These guys have 65,003. Okay. From the applications that are sitting in this VPCs, in order for them to get to the on-prem environment, what route they are going to take, right? So since we are receiving 10/8 to this transit, and we are receiving 10/8, this transit is receiving 10/8 from the on-prem and also from the other transit. From on-prem, it is receiving with ASN length of 1, just 65,000. While from its partner, which is the transit peering, it's receiving with the AS path length of 2, AS path length of 65,003 plus 65,002. So which one it's going to prefer? Definitely it's going to prefer the locally attached, the data center over here. So its preferred best route is going to be in this direction for 10/8. What about, let's say, if I want to call this as a GCP and this one is AWS. GCP is going to prefer its local transit and like local data center, and AWS is going to do pretty much the same thing on this side too. So the applications which needs to get to 10/8, it's going to go to the transit and transit to the data center right away, right? So that is going to be the best route possible. All right, so what is going to happen if you are going to lose this connectivity somehow, right? So for example, if I'm going to lose this thing completely, at that point, the application that needs to get to the 10/8, what route they have? Now, the best path possible is through 2 ASNs, which is 65,002 and then 65,000. So if I want to draw it with the orange, then the application sitting over here in this VCP is going to take this route, and then is going to get to the data center. And from there, if it has to go back to the other data center or whatnot, it can utilize the MPLS link or not, right? So that is going to be our best possible path. All right, now, what about if you are, let's say if this connection is back up, right? Let me do this. This connection is back up. There is no problem with the connections. But what you are doing at this point, you are actually prepending the AS path over here. For example, if I use it with a different color, that I'm saying 65,001 and 65,001. So I'm prepending it like 3 times over here. In this scenario, the application sitting over here, what it's going to do, it is still going to prefer this route. Why? Because the transit is going to receive 10/8 via AS path length of 3, while it's receiving 10/8 with the AS path length of 2 from its peer transit. So 65,002 and 65,000 only 2. So this path would still be a valid path in this scenario, even though there is no there is no degradation of service, there is no disconnectivity or anything like that. So that is how you can actually utilize the traffic engineering capabilities of Aviatrix controller. All right, so let's talk about the failover scenarios now. So let me just erase this one more time, and then when I come back, we'll talk about the failover scenario, how the path is going to be chosen by the Aviatrix controller or the gateways. So let's talk about that. All right, so let's discuss the failover scenario. For example, you have spoke VPC with 2 Aviatrix spoke gateways, and then you do have transit with Aviatrix transit gateways. You already have ActiveMesh like this. There are some applications sitting over here in that particular VPC, and it wants to communicate with the outside world. It could be the other VPC or maybe on the internet. Let's say here is the application, right? At the steady state, when everything is up, both tunnels are up. For example, this is, we want to call it the tunnel 1, and this is the tunnel 2 at this point, right? So both tunnels are up at this time. So if the traffic path, if I wanted to draw it out, then it towards the transit, then this application to like this, or it could be through this to this particular transit gateway. So it has 2 different paths available for this application to get to because of the ECMP nature between the Aviatrix spoke gateways and then the transit gateway. So now let's talk about it. What is going to happen when we are going to lose one of these tunnels, right? So for example, if I'm going to lose this tunnel completely, then obviously this path is going to go away, right? So this path is going to go away, but the other path is still available, right? So what's going to happen, the spoke is going to receive the traffic again, and instead of sending over to tunnel number 1, it will continue to send it over to tunnel number 2. There is no reconvergence, meaning the VPC or VNet or VCN routing table is going to be intact. Nothing is going to happen. The spoke gateway is smart enough. It knows that one of the tunnel is down. Controller knows that one of the tunnel is down, but gateway is going to just switch the traffic over to the HA gate transit gateway, which is the tunnel number 2. So all good at this point. So what is going to happen when the second tunnel is also down, right? If I'm going to create this, right? So basically this route is also gone. At this point, what this gateway is going to do, this gateway is now this gateway knows that both tunnels are gone. It's going to use the interconnected link between them, right? And then the path is going to be from here to either this guy or from here to either HA gateway. So far, everything is good because we still have a path, and then we are still getting to the transit. From transit, there could be other spokes or on-prem connectivity. At this point, it doesn't matter as long as we send the traffic over to the transit gateway. So what is going to happen if the entire spoke gateway goes down? The application is still sitting over here. It wants to communicate to the transit gateways. Now both of the tunnels, which was coming from the primary spoke gateway, are down. But we still have connectivity with the transit using the HA spoke gateway with these two tunnels. Now at this time, controller knows it about the entire gateway is down, which basically means both tunnels are down. And then what controller is going to do, it's going to invoke an API call to the native APIs of any of the CSPs. And the RFC 1918 routes, the summary routes that we talked about in the previous sessions, they will be actually now pointing towards the HA gateway. So there was some of them were pointing towards the primary, and then some of them were pointing towards the HA gateway. This time we are going to switch that, and we are going to say, okay, so summary routes for which were pointing previously to this particular spoke gateway are now going to be pointing towards the HA gateway, so the communication is going to be restored. So only 50% of the communication is going to be disturbed at this point, but as soon as the API call is made, the RFC 1918 summary routes are going to be pointed towards the HA gateway. Everything is going to be restored right away, and then the traffic flow is going to be like this. All right, so that's all I have for today's session. In the next session, I'll be discussing about the active standby feature. That is a feature which you might need based on your use case, where you want Aviatrix transit gateways to act as a active standby for the on-prem connectivity. Thank you very much for watching.